Want to make sure everybody can see what we're presenting here. So, all right, I think we've got Matt's slide, or excuse me, Ralph's slides. Matt's got those up. And we'll get your presenter view back and we should be good to roll.
Great.
Thank you so much.
All right. All right. So thank you all again for being here, the opportunity to speak to you. So here's the agenda. Talk a little bit about myself, get that out of the way, thankfully. Then I'll speak about some of the challenges facing the supply chain, more broadly, of course, with the audience here. None of it will be unfamiliar to you. Then I'm going to talk through what I call the pyramid of supply chain analytics capabilities and talk through how you could potentially use open source technologies to use those types of analytics. Then I'm going to go into some use cases for analytics and supply chain management, do a demo of how you can actually design your supply chain using some of these tools, and then some question time. All right, so about me, I grew up in Indiana. I went to college there, and after graduation, I joined the military. I like to tell people that I majored in physics. I realized about 3 years in, I wasn't all that good in it, so I joined the Marines. I was on active duty, where you don't need to know that much physics to be a good Marine, surprisingly. I was on active duty for about 7 years, and I've been serving as a reservist since then. While I was on active duty, I actually met an Air Force officer who had received his bachelor's degree in what's called operations research, which I never heard of this field, but essentially operations research is a grab bag of different types of math that can be used together to solve real world problems, which was really appealing to me because I actually enjoyed the math side of physics more than the physics side of physics. And so when I started looking into this field, I decided to go back to school and get my master's in it. After I left active duty, I relocated to Minneapolis, being near my wife's family, and was pretty shortly hired at General Mills to be a supply chain designer. So what that essentially means is, we'll go into more detail, but at General Mills, I was mostly doing projects around where should they put their distribution centers for the different types of products they make, what customer DCs, so customers in this case being like Walmart, Kroger, Target, how should we align those to the General Mills DCs? Did that and then a little bit in the manufacturing side and a little bit in international supply chains as well as they were acquiring different companies abroad. Got recruited to come downtown Minneapolis, work at Target, and I worked there for about 6 years, primarily doing e-commerce network design. So including recommending how to expand the ship from store network. At that point, it was a pretty small portion of Target stores were being used to ship e-commerce orders. I helped recommend what stores to incrementally add to that. And then later how to do last mile delivery networks in urban markets. Last year, I really saw the need for more industries, more companies to have the use of supply chain analytics in their companies. So I decided to step out on my own, start my company, and it's really been my honor to help about a half dozen client companies so far across various sectors improve their supply chain through analytics. And in addition to running my company and serving the Marine Corps Reserve, I'm also an adjunct at that other college in the B school where I teach stats. And I like to tell people I've loved maps and math and computer programming since I was a little kid, kind of weird little kid liking all those things, but thankfully managed to find a job that allows me to merge all those together. All right. Okay, so given the makeup of the attendees here, I really don't need to belabor the point that the COVID-19 pandemic has caused unprecedented disruption to the global supply chains. Manufacturing shutdowns, labor shortages, and a dramatic shift of consumer spending from services to goods has really changed the previously invisible flow of goods, which of course is not invisible to those of us in this audience. It can be seen, of course, in disruptions off LA Long Beach, which have thankfully abated. The current rate hikes that the Federal Reserve is enacting now to try to stem inflation, baby formula shortages, wheat shortages, which are causing food price spikes globally, as well as home repairs, home construction, for those of you who might be in that business. One thing that I would recommend is if you've not heard of this book called Arriving Today. It recently came out. It's by a Wall Street Journal writer named Christopher Mims, and he describes global supply chains all the way from sourcing and manufacturing in East Asia to the delivery of consumer goods. So while my background is not a traditional supply chain management professional, as a data scientist, I am proud to use my skill set to aid the efforts of supply chain professionals like the group assembled here today. Okay. So you may be asking yourself, how can analytics be used in supply chain management? Depending upon your background, this slide might be old news to you, but I find it is useful to describe supply chain analytics in the framework of descriptive, predictive, and prescriptive analytics. Now, descriptive analytics, the biggest and most important part of the pyramid, and thank you, Molly, for going deeply into that, includes business analytics and diagnostic analytics of the supply chain. You know, how many of my trucks arrived on time? How productive were my plants? How about my warehouses? Are any of these how are these metrics trending, and are any of them worrisome? Next is predictive analytics. What's going to happen in my supply chain? How do we predict what is going to happen next? That includes things like sales forecasting, as well as forecasting costs of your supply chain inputs, perhaps using linear regression to help understand trends and the relationship between metrics, and then certain types of supply chain simulation and statistical process control would also fall in this space for those of you in the manufacturing space. Top of the pyramid, which by volume should occupy the least amount of your time, is prescriptive analytics. What should I do with my supply chain? So this includes things like supply chain network design, which I'll talk about in detail later, inventory optimization, manufacturing optimization, and supply chain simulation. Now, what's not on this image, but is fundamentally important, is that there needs to be a solid foundation of data management, data integrity, and data availability, because otherwise none of these activities are sustainable or repeatable, really. Now, a key point for this audience in particular is that open source technologies are really changing the landscape in supply chain management and supply chain analytics. If you work with open source programming languages like Python or R, you may be able to mentally pick out what packages you might use for these kind of activities. Now, this really is a sea change from when I started in the supply chain analytics field a decade ago after I left the military. Back then, when I first started at General Mills, to execute any kind of project, you really need kind of a grab bag of different commercial software to do anything. So perhaps you needed Excel for data prep and data analysis. You might need something like SPSS or Minitab for statistical analysis. To do any sort of data visualization, you need something like Tableau or Spotfire. And then if you're going to do things like supply chain network design or supply chain simulation, there was a very limited number of commercial vendors like Llamasoft. And to do anything, you really had to figure out how to put all these things together, and it's very time consuming. Now with a talented data scientist, you can consolidate these capabilities into a single language, like Python, like R, like Julia, and do all of these capabilities within more or less consolidated workflows. And this really leads to greater productivity across the board within an organization. Now, given that there are IT professionals in this room and on this call, I'm going to be careful about my words here. Open source does not mean zero cost. Right? It's open source is free as in speech. If you're familiar with that notation, meaning that open source technology, you can change it, you can you can adjust it to your needs. But it's not free as in beer, meaning it's not without a cost. It's more like free as in cheap Wisconsin beer, right? So even though I'm not originally from Minnesota or Wisconsin, I still have to put in some digs on the PBR if I can. So just be aware that if you do use open source technologies, as you scale up, there is going to be a burdened cost, both on the hardware side and potentially on the software side. It's quite possible that open source alternatives could be cheaper than commercial alternatives, but it's not free lunch. Okay. All right. Now I'm going to talk about some common supply chain problems that can be addressed using analytics. Not meant to be exhaustive, but just some that I've personally done or personally seen. And these are going to have some detail change, and they'll be in a case study format. Okay, first question is, if you're going to have a single DC, where should it be? Okay, so the client was a national diversified manufacturer, and I received a phone call from my contact at this at this manufacturer on late afternoon saying, have an issue. We just got kicked out of one of our regional DCs. We were given 30 days notice that we need to get out of it. And so we need to find warehousing space quick. Can you help us locate where we should start searching for commercial real estate? So talked the next morning and they said, I talked over some of the details with them. They said, great, can you have something this afternoon? I said, maybe. Said, if nothing else, I'll have it to you tomorrow afternoon. And so what I did was called a center of gravity study. And if you're in supply chain network design, you can Google center of gravity study. And the Googleable way essentially says, find a table with your demand points, whether it be your individual customers or your sub warehouses, and then find the weighted average longitude, find the weighted average latitude. There's your center of gravity. That's what Google will tell you. Google will be wrong. I will tell you that. And what I did for this client was I used what's called nonlinear optimization. And this client's not in Wisconsin, they're elsewhere, but just as an example, I took 16 cities in Wisconsin and did a center of gravity study using the traditional Googleable way. The center of gravity is right around here. So that traditional way was on average 51 miles away from the demand points, 51 miles. Okay. Using nonlinear optimization, which took me 2 hours more to do, found that the actual optimal center of gravity is in Wauwatosa, 44 miles away on average, 14%. Is it worth spending 2 extra hours to get your warehouse 14% closer to your customers? I would say it is. All right. So if you're doing a center of gravity study, take the time to do a little bit of nonlinear optimization, and you can do this in R Python quite easily. All right. Next up, what if we don't have one distribution center, but we have multiples and we want to know where they are? So the client here is a national direct-to-consumer, which is another way of saying e-commerce, vitamin and supplement manufacturer. They were introduced to me, and basically they're on a real growth path, which is great. And right now they have a bunch of leased 3PL DCs, and they're going to reach capacity in a few years. And they're saying, hey, Ralph, where should we set up our DCs in the future? Do we have them in good locations? And if we do, where else should we be building? Or if not, where should we be leasing in the future? So did what's called a greenfield analysis. Now, greenfield analysis essentially says, if I'm going to have one DC to support my demand, where would it be? Exactly the same as we just talked about. But it can also, then greenfield goes, if I have two, where should those two be? Now, when you have two DCs, when you're going from 1 to 2, you're not going to just add on another location. So like if you have a national continental United States demand, if you're going to have one DC, a center of gravity study would say somewhere in Missouri, or roundabouts, center of the country. If you have two, there's going to be one in Pennsylvania, support the East Coast, one in roughly Nevada, support the West Coast. So that's free advice to you. But you need to realize Pennsylvania and Nevada, neither of them are in the middle, right? So if you're going to have one DC, that's a different answer than if you're going to have 2 versus 3. And so a greenfield analysis says, if I'm going to have 1, 2, 3, 4, 5, what are those locations? And then how far on average would my customers be to the closest distribution center in those? And so for this particular client, it actually confirmed that their current DCs were in good locations. So that was good to hear, good to tell. And I suggested them, as you're growing, if you need more capacity, this is the next location that I'd recommend you try to find some warehousing space in a couple of years. It is important to say that greenfield analysis is intended for strategic discussions. It's not intended to be an end-all be-all, but it's something that can be done quickly and leads into more detailed activities. And it's important to say that there's a couple types of greenfield analysis you can do. One's called a pure greenfield, which is exactly what I described. Start over. If I didn't have any, where would I put them? The other kind, which I actually find to be more beneficial for my clients, is I call it a modified greenfield, which is essentially to say either my current DCs, I'm going to keep them, or some subset of them, I'm definitely going to keep. Where should I add on to those? Kind of saying there's 2 different starting points for my decision-making process, and there's 2 different ways you can approach it. Both are considered greenfields. All right. And so you may be wondering, like, how do you actually compare the results of these different greenfields to make a recommendation? Well, this is the pure greenfield from this particular client. If they were to have one DC, you actually can say, well, on average, how far are the customers from the distribution center? One DC, on average, they were 850 miles away from their customers. Okay. With two DCs, it drops down to a little over 500 miles. Three DCs, 400 miles, and so forth. The more DCs you get, the closer on average you are to your customers, if you're picking them well. Now, this is called an elbow plot because it sort of resembles your arm, your elbow, if your elbow is more like a line. And so when you do an elbow plot, what you actually see is that as you add more distribution centers, eventually that crook in your elbow shows the point at which adding more distribution centers may add warehousing capacity, but it doesn't actually get you closer to your customers. And so for this particular client, said, between 7 and 9 distribution centers is probably, in terms of metropolitan areas, probably about the maximum you should be considering, because any more is not going to get you any closer. All right. Last one for network design. So we talked about greenfields. We talked about center of gravities. Now, what if you have a distribution network or a manufacturing network and you have actual real world constraints on them? Like, your warehouse can only fit so much inventory or your plant can only produce so much. What do you do? How do you make decisions strategically about your supply chain? And this is what's called network optimization. You can do this with commercial software. There's a pretty well-developed ecosystem there. You can also do it with open source. And this particular client, this project I just started, they're a B2B e-commerce distributor. So they're doing e-commerce, but it's only B2B. And they're asking me, hey, how should we change our import network for our imported products? And so doing essentially a large-scale optimization model plus greenfield for this particular client. Okay. All right. Next, talk about manufacturing optimization. So if you're looking within the four walls of your manufacturing plant, you may wonder, hey, how can I actually get more capacity? You can do this through optimization modeling. So this particular client's CPG company, and for one of their product lines, a pretty significant portion of their product they have to outsource to a contract manufacturer because they had insufficient capacity in their main plant. And so they asked me, hey, how can we actually increase productivity in this main plant without significant capex? Because of course you can always add another line, right? That's very, very pricey. Is there a way that we can actually get the productivity higher out of this plant without investing as much? So built an optimization model for them, and basically it generates a production sequence for each of their product lines and on each of their lines. And given the nature of their product, like not every product can run on every manufacturing line, just like any other manufacturer. So taking into account those things, changeovers, all the nuts and bolts considerations. The impact was, and then at the end kicks out a spreadsheet for them to use. And the impact was about a 10% increase in production capacity identified out of this plant as compared to the current planning methods. And this is all just using optimization analytics. So that top of that pyramid. All right, another one, inventory optimization. So this is for a organization that they're not like a car rental or anything, but they're an organization that maintains a fleet in support of their work. So you can think of any maintenance company, they maintain a fleet. Well, the fleet maintenance portion of this organization, they're national, and they have essentially the same fleet, but they have very inconsistent inventory management policies. And so what would happen is that on their repair parts, they kept repair parts in stock for their fleet. They would have simultaneously in one location have a shortage of a repair part and another location have an overage of that same repair part. So they, water everywhere, not enough to drink. That's exactly their situation. And so that led to a lot of their vehicles being down unnecessarily when all they needed was just better inventory management of their parts. So what I did was ABC analysis, and then after that did statistical demand pattern modeling. traditional supply chain textbooks will tell you that demand for end items or consumer products is normally distributed. Very bell curve. Not true. Actually, most products are not normally distributed. And with this particular organization, their consumption of repair parts was very differently shaped. So you can actually look at the consumption of repair parts or consumption of consumer model products and say, what statistical distribution best describes my consumption? And once you do that, you can actually then set your safety stock targets based upon that. So, they had 10% of their SKUs were driving 90% of usage. I told them that Pareto on steroids. That was funny given the people I was talking to. They sold steroids, so yeah. All right, so some other capabilities. This is not something I've actually done, but this might be useful. Delivery route optimization. So let's say you're doing DSD routing. So in consumer goods, DSD is called direct store delivery. So if you go to a grocery store, bread that's on the shelf, the Cub or Walmart or whoever, they didn't actually put that bread through their own warehouse. The bread manufacturer delivered it directly to the store. That happens very commonly with bakery, snack foods. So Frito-Lay does that. Soft drinks, the Coke distributor just takes it directly. And so the question is, given the ad of several hundred delivery points and 7 distribution centers across the tri-state area, how do you actually optimize your delivery routes? And this includes things like delivery windows. Maybe a store is only open from 10 a.m. to 7 p.m. or whatever. Vehicle capacity, of course. Driver shift times. You don't want to have a driver going too long. How do you do that? There's a combination of network optimization, which kind of defines service areas, and then what's called the vehicle routing problem. Even though the field of operations research, my academic field, the name of the subject is not all that useful because it really doesn't tell you what you're doing. Some of the sub-problems, like the vehicle routing problem, are actually very self-descriptive. So there's ways to optimize delivery routes. Some other uses of this kind of approach: scheduled inspection and preventive maintenance of industrial things. So I actually talked with a company that they don't make commercial HVAC, but they do contracts with big box retailers and other companies to go around and do inspections and preventive maintenance. So like they'll go to a Walmart every 3 months, climb on the roof, take the filter out, replace the filter, make sure everything's good to go. And they were wanting to know how actually can you improve their routing of their technicians, so they were literally driving from North Dakota to Montana, back to North Dakota, back to Montana over the course of a week. Yeah, not a good idea. Refilling cash in ATMs. I actually just read about that recently. And e-commerce home delivery, which was my bread and butter at Target for a long time. All right. Give you kind of a visual of what's possible. So you have 300 deliveries across Metro Milwaukee, and you just have a single warehouse there in the middle. You have 6 delivery vehicles. Each can hold 55 deliveries, so 330 deliveries. How do you design your delivery routes within the capacity constraints such that you are minimizing the longest route? So you want to make that longest driver route as short as possible. That's your goal. Luckily, Google has made a Python package that anybody can use, which does exactly this. Right. So from here to here, and you can see that the shortest route is that yellow route, which is core of Milwaukee. And you have 2 long routes that are about equidistant, which are the green and the blue routes, which go to the exurbs and the suburbs. So this is a very simple example because it doesn't include things like delivery times and shift times. But these are some of the capabilities that are readily available and actually not that hard to program if got a handle on using Python. Okay. All right, I'm finally caught up on my time. All right. So going to transition now into a demo on supply chain network design. And First off, what is supply chain network design? It's the strategic analysis of the locations and activities of the various firms of elements of firm supply chain. So if you're a manufacturer, that includes, where your warehouses for your raw materials, your semi-finished and your finished. If you are a third-party logistics distributor, where should you put your warehouses to support, your potential customer base? If you're a retailer, how should you use your stores as a link in your supply chain? So, like I mentioned, big portion of my time at Target was in the understanding how to use stores as hubs for e-commerce delivery. That's a big question. That's a supply chain network design question. And so supply chain network design seeks to understand these big questions, all with the intent to understand the impacts on profitability, cost, service, and other key metrics, and with a goal to minimize or maximize one or two key metrics, usually cost or profitability, but post-COVID, more emphasis on things like reliability, risk diversification, and things like that too. So we'll transition shortly to the web-based app, but first I'll introduce the scenario. So Heartland Widgets, I'd love to speak about widgets, not because I'm an economist, but because I wish I was. So you're a supply chain data scientist at Heartland Widgets Incorporated. Your company's market leader in widget sales across an 8-state area of the Midwest. Pandemic-induced shift in consumer demand for services to goods, as well as stay-at-home orders, has led to a boom in demand for your company's flagship product, the at-home widget. Luckily, Heartland's 2 factories in Milwaukee and Indianapolis have 2 million units of capacity, 1 million apiece, for 1.3 million units of demand across the Midwest. However, the company's 3PL DC leases expire next year, and the company wants to move into an owned DC model. The Director of Supply Chain Strategy has asked you to reimagine the company's distribution network. You're to recommend Heartland's manufacturing volume by plant, where to place its DCs, the DC to customer alignment, and all to minimize costs, because of course cost matters. And depending upon who you are, the scenario might actually strike pretty close to where you are today. All right, so how do we do this? Optimization modeling. Optimization modeling, broadly speaking, allows a practitioner to take the real world, represent it as a series of numbers and equations, and where these numbers and equations reflect a set of interconnected decisions. And these are also constrained by real-world limitations. Special software takes these representations, which is called an optimization model, and then solves that math problem and returns the set of decisions that optimizes, minimizes, or maximizes the expression that includes some or all of the decisions as inputs. So what are the decisions that we need to do in Heartland? We need to decide where to put our DCs, what customers to align to them, what plant should service which DCs, and how much volume each plant should produce. Now, these are all interconnected decisions, because if you align a customer to a DC and then align that DC to that plant needs to produce the volume for that customer. These are interconnected decisions. And it's very difficult to work through all of these interconnected decisions to come up with an ideal or optimal solution without optimization modeling. So let's talk through some of the different supply chain costs that Heartland is facing. All right. I'm intentionally leaving out the plant opening cost because we have 2 plants. We can treat them as a sunk cost because they're in existence. We have a manufacturing cost. We're going to treat that as 15 cents per unit. And all of these are intentionally simplified. In real world, of course, it's not that simple, but let's say it's 15 cents per unit, whether you're producing at Milwaukee or Indianapolis. Then, once we've produced it at the plant, we need to get it to our distribution center. We're going to say that that is 5 cents per unit mile. Now, a unit mile is moving 1 unit, 1 mile. If you move 5 units, 10 miles, that's 5 times 10, or 50 unit miles. So that's our plant to DC cost. Then, once it's at the DC, we need to pay to open these. We're going to an own DC model. So we're going to price these at $1 million a piece, wherever they are. Again, commercial real estate is not the same everywhere, obviously, but for simplicity, let's say $1 million a piece. Once it's at the DC, we got to pay handling costs. We're going to assume that's just 1 penny per unit, no matter where they are. Once it's off the shelf at the DC, we now got to get it to the customer. And we're going to assume that we can't use as efficient trucks. So this is going to be 15 cents per unit mile to get to the customer. So all the way from coming off the factory line to getting to the customer, those are all the costs we're incurring. That is our total supply chain cost. Now, depending upon where you are in a supply chain organization, one or maybe two of these are your priority. But when you're designing a supply chain, looking at the total cost, you should consider all of them together. Now, one of the tenets of supply chain design is that these cost components can be inversely related to each other. And this is where it's hard to fathom sometimes. The more distribution centers you have, the closer you are to your customers on average. So if you're closer to your customers on average, you're going to spend less on getting the product to them. This component will be lower. However, the more distribution centers you have, the higher this is going to be, because you got to build more of them, right? So as your DC to customer transportation cost goes down, your DC opening cost goes up. They're inversely related. And so when you have these kind of competing cost structures inside your supply chain, for us to actually understand how these relationships work together and then come up with an optimal solution, we really do need to use optimization modeling. Okay. And with that, I will cut over to an app. Actually, one more slide, sorry. So this app's written in the R programming language, and it's using a package called Shiny, which is a visualization package that allows you to build web-based apps that have the analytical horsepower of R underneath it. Sorry, I messed this up. The logo's got it. Okay, got it. So the logo is that, not that. My kids have moved on to Encanto, but every time they sneak into my office, I say Shiny, and they want to watch that song on my phone. Okay. All right. I don't know if people online can see this or not, or what I need to do. Okay.
I'm just going to make this available so that our online folks can see it as well. So bear with me for 1 second here.
Does anyone have any questions for Ralph before we move over to the demo? And then a reminder for those online, you can also use the live Q&A as well as we're getting this pulled up. Of course you do, Tristan. I'm glad you came today.
I don't think so. I mean, I think I have one.
So my biggest questions, in looking at your model, I understand, you broke out, say, transportation, origin, transportation to the customer. But how are you determining what that 5 or 15 cents per unit is? Because there's lots of different things that can go into determining what that is.
Yeah, I mean, in an actual project, you're usually working with freight procurement. People saying, hey, from here to here, can you price this lane? Or do you have historical costs? Or if they're using a third-party freight brokerage service for that kind of information. That's how it actually goes in.
So you're doing that for all so if you're trying to optimize the placement of a DC, the difference, whether it is on this side of an area or the other side, can have a huge impact in that. So are they pricing out both options, or to what point are they pricing it out? Because you could put it anywhere in 1,000 different places.
Yeah, so if you're looking at, say, a metropolitan area, usually the freight rates, at least in terms of over-the-road trucking, it's going to be identical. Right? So like you could treat all of Madison as the same when it comes to the cost component of the trucking.
I did.
Now, all of Madison may not be the same in terms of the commercial real estate availability or the cost per square foot of a DC. And that's where you got to understand the granularity of the differences between different parts of the metro.
Yeah, well, as your scope broadens, whether you're in a head haul location or a back haul location will have a huge impact on your transportation. How close you are to an intermodal hub, those types of things, how close you are to certain freeways can make a difference in those calculations. And I'm just, part of me is trying to understand when you're looking at something like that, how broad it is. And then in a more regional area, is it dedicated or asset or broker? So those, so I'm just trying to understand, because that is a key component that I think gets overlooked a lot, besides just labor cost, property cost and things like that, because that transportation becomes an ongoing charge, especially today. It's a bigger challenge.
Oh yeah, absolutely. I mean, that's why these projects take several months, because there's a lot of those conversations with different procurement people saying, okay, now in this component, is this going to be significantly more than this one, because we don't need to pay an intermodal drayage because this one's already at the intermodal port versus this one isn't. So that's exactly the kind of conversations why these projects do take quite a while.
And I think as you get into your demo, we'll see a little bit of the behind the scenes raw inputs, right?
Mhm.
So to your point, each of those single file categories can have its own double click, or I'm going deeper on
Those based on which port am I coming into. Handling costs the same way, right? So depending on what type of product I have, my handling cost could be huge or small, or how am I balancing that out? So yeah, there's a little bit of a double click within each of those too. It's a good point.
So for example, I prepared a bunch of CSVs, put them into a zip file, and I'm going to use these for the inputs. And this is just a publicly accessible website. Again, with Shiny, it's just a JavaScript-based UI, and it can either be deployed internally on your own server, or you can put it on a public thing and put some password protection behind it. So I've uploaded it. So let's look at the inputs. We have 117 customers across the Midwest, all the way from Rapid City in the west to Fort Wayne, Indiana in the east, my home of Hammond, Indiana, right there. And the demand is proportional to the population. So 1.3 million units of demand across the Midwest. If you have, so this maximum distance to DC, it doesn't come into play here, but in network modeling, you can say, I want my customer to be no more than 400 miles away from a distribution center. Very, very much the case if you're doing any kind of perishable food modeling. Very, very common to do that, but not going to play in here. Plants, we have 2 plants, Milwaukee and Indianapolis. Each of them have 1 million units of capacity. And then for potential distribution center options, I've listed the 20 biggest cities in the Midwest. And to your point, if you had in one location, 7 or one metro area, 7 different potential locations, you could put all 7 in, and they all have their own individual cost components. Yep. Customer demand for the widgets, skip through that, handling costs. Okay. Everything we just described to in terms of cost components got put in there. Gonna skip that, gonna skip that. All right, click the go button. All right, so what's happening behind the scenes? All these inputs from our supply chain that we've uploaded and reviewed, the code is now making into a math problem. It's sent to a solver. The solver solved the math problem and then gave the answers back, all in the time it took for me to describe what it's doing. Okay. Because it's a demo, not all the time in real life, I'll say that much. All right, so what does this look like? So we'll start first with the customer flows. Okay, so we have 6 distribution centers. That's the optimal number of DCs when we look at a total cost. So we have Omaha, Cedar Rapids, Chicago, Indianapolis, Milwaukee, and St. Paul. And you can see that their coverage areas are roughly geographical. We don't have, DC and Cedar Rapids serving a suburb of Indianapolis or something like that. Okay. So that's the DC to customer flows. Now our plant to DC flows, the Milwaukee plant is servicing 5 of those 6 DCs. The Indianapolis DC is being served by the Indianapolis plant. What's kind of odd is the Chicago DC is also being serviced by the Indianapolis plant. Why is that? Chicago's a lot closer to Milwaukee than Indianapolis, as somebody who's driven that quite a bit. A good portion of my family's still in Indianapolis. So. Okay, so let's look at what this cost structure is. Total supply chain cost, and this is optimal, meaning minimal in this case. Have a pointer? No, it's not. Okay, sorry. Top right, minimal cost, 22.9 million. Okay, so that's our minimal supply chain cost here. The components, our DC opening cost is $6 million for 6 DCs at $1 million apiece. Our plant opening cost is 0 because we're treating that as a sunk cost. Manufacturing cost is minimal, $200,000. Our DC handling cost over here, also minimal, $13,000. The big players here are our DC opening cost, our plant to DC transportation is 8.6 million, and our DC to customer transportation is 8.1 million. So that's coming up to roughly $23 million. You can look at the individual volume flows if you care to, but why are we seeing volume flowing from the plant in Indianapolis to the DC in Chicago? Well, let's look at product utilization here. Milwaukee's capacity is 1 million units, and it's producing 1 million units. Indianapolis has a capacity of 1 million units, and it's producing 300,000 units. Okay. That may be a clue that Indianapolis is a bad location for our plant, given our demand, or maybe we need more CapEx in Milwaukee, or both. So that's why Milwaukee's being capped out. That's why we have to do these flows. So that's our minimal scenario. Please take a note of that 22.9 million figure. All right.
I'm going to have you go on the microphone.
So if you're looking at expanding your business because you have this excess capacity, either A, it tells you where you want to go to utilize that, or if you're going to go someplace else, that yes, you want to move your production if that doesn't look like it's going to be a fit for you anymore.
Like maybe Louisville and Lexington, Kentucky are good markets for you since they're so close. Okay, so I'm going to make a small detour to explain more by what we mean by constraints in supply chain design. So in optimization modeling, a constraint is a mathematical limitation on what set of decisions you can make in real life. So just like in any sort of decision in life, the more restrictions you have on it, the fewer options you have. And so optimization modeling, including supply chain network design, is an exercise in understanding the trade-offs involved in making constraints more or less restrictive. Tighter or looser is the term of art. And so in designing your supply chain, the tighter the constraints, the more restrictive they are, the higher your total cost becomes. Maybe not by much, but it's going to get higher because you just have fewer choices. And so supply chain design is partly an art around understanding the additional expenses associated with tighter constraints. And we'll talk through one of these now. So we just saw that the lowest total supply chain cost occurs at 6 distribution centers. So what happens if we actually force our model to have exactly 3 distribution centers? So we're adding that additional constraint. So here's pretty straightforward. We have this little setting that says include min-max DC constraints. Going to set it to a minimum of 3, set it to a maximum of 3. Click go. It'll build that math problem in the background, hopefully solve as quick as I'm hoping it to. Okay, there we go. All right. Anybody want to take a guess where these 3 distribution centers are going to be? Okay, Milwaukee, Chicago. Okay. There we go. All right. Minneapolis, Chicago, Indianapolis. Yeah. Okay. All right. So again, we're forcing it to have exactly 3. So we're seeing 3. That's good. Otherwise, there'd be a problem. And there's a regional component again. The Minneapolis DC is essentially getting everything west of central Iowa, getting all that spread out, which are pretty low demand, by the way. Not a ton of people live in Rapid City. Not a lot of at-home widgets being sold out there. And again, we're seeing product being flowed from the plant in Indianapolis to the DC in Chicago because of that insufficient capacity. Now let's talk about cost. Our DC opening cost is now $3 million. So we just saved $3 million because we have 3 fewer DCs. However, our total cost is now $27 million. We just went up $4 million. I believe it's 18% from I remember my slide properly. So by adding that constraint, our cost went up $4 million, 18%. If we were lucky, it would have just gone up a tiny bit. Unfortunately, it went up quite a bit. And so the puts and takes are DC costs went up, but our transportation costs went up. DC opening costs went down, our transportation costs went up, and our overall total cost is up 27 million. So, shoot. Actually, could we go back to the PowerPoint? I'm not sure if it's possible. I want to show that, not more DCs, that curve thing. Okay. Now, the thing about when you put in constraints like, hey, exactly 3 distribution centers, is you don't actually know what the results are going to be until you look at them. We could have seen something where the result was $13.1 million. So $200,000 more, not a significant difference. Or it could have been a lot more like it was. And so it's really hard to say how will additional constraints necessarily change my results until you actually look at the results. And thank you. Sorry for that. Okay. And so, if you have a model that runs as quickly as this, you can actually look and say, well, what if I did all these different potential options and just compare? And so what I'll show is we just did a constraint around exactly 3 distribution centers. What I'm going to do next is say, what if I had exactly 2 and force that? What's the minimum cost? What if I had exactly 4? What's the minimum cost? All the way through all 20 potential distribution centers in the Midwest. What does that look like? How do those things compare? Okay. All right, and this is what it looks like. So each one of these lines, each one of these colors reflects a different component of our total supply chain cost. And the x-axis is the number of DCs that we're forcing the model to take. The y-axis is the cost of the component in millions of dollars. The kind of, I don't know, is that fuchsia? Whatever the top color is, that's your total cost. So it's just the sum of each of the components. Now, at the bottom, our manufacturing total cost and our DC handling cost is virtually nothing in the grand scheme of things. And it's the same no matter how many DCs we have. Because, again, we don't have differential cost per DC, unlike real life. Our light green cost here is our DC opening cost. And since it's $1 million per DC, it's just steadily sloping line upwards to the right. And $20 million for 20 million DCs, $2 million, 2 DCs. What's really interesting here is how our transportation costs vary. So this blue line is our transportation cost from our plants to our DCs. And it's pretty stable. Like, it actually doesn't really cost any differently to get our product from, well, a little bit more for 2, but like 7 DCs to 10. However, when we look at our DC, our customer, DC to customer transportation cost, that declines. Remember that elbow plot from our greenfield? Looks pretty similar, huh? Because we're looking purely at distance to the customer. So as we go up, as we go from 2 to 20 DCs, our DC opening cost rises. Our customer, DC to customer transportation cost declines. And our total cost has an inflection point. It declines as we go from 2 to 3 to 4 to 5 to 6 DCs. The minimum total supply chain cost is 6 DCs, as we saw initially. But between about 4 and 9, it's not all that different. Between 4 and 9 DCs, it's only about 10% higher than with 6. And so if I was doing this as a real study, you present options saying, this may be your minimal cost, but you actually have a number of different options that return roughly the same total supply chain cost. I know I'm a little bit over time, so there's another scenario in here that I can just show real quickly the slides of it. If you actually wanted to add capacity to Milwaukee, you can change that and you say, hey, if we added another 500,000 units of capacity to Milwaukee, what does it look like? Now suddenly the plant in Indianapolis is only servicing its plant warehouse. Plant in Milwaukee is servicing everywhere else. And you save about $500,000 in total cost. Now, whatever the CapEx says would be for that, who knows if that actually is more or less than that $445,000 savings. But supply chain modeling can be used to do things like evaluating return on the investment for CapEx in a plant or a distribution center. And this can be done, quite easily with, commercial or open source software on that. All right, that's about what I have to say. Thank you all.
Great. What other questions does everyone have for Ralph?
Hi, Ralph. How everybody? My name is Mario. Thank you for your presentation. Do you focus on any causal analytics? I know that you focus on causal analytics, seeing if there's any inputs impact the actual outcomes.
Yeah. There's definitely a line of diagnostic analytics and saying, as my cost inputs are trending, how do they actually impact the overall bottom line? Yeah, that's something I've done.
Okay, and you do like A/B testing on it as well, or
not A/B testing because there's really, that's usually something that's more well suited for internal teams simply because they can do consistent monitoring.
Right.
But it's more with and without this particular factor. How would the impact?
Right.
How would impact the thing?
Okay. Thank you.
Great. Other questions?
So you run through the first scenario and you're looking at, your elbow and you say there's the difference between, say, that sweet spot or whatever is that 4 to, let's say, 7 DCs. Is there a way, once you've looked at that and said, okay, here's the optimum location, to go back into your total customer transportation costs and say, okay, Chicago plant, the actual cost for delivering out of there is 23 cents a mile, and it varies around down to 11 cents a mile. Your average may still be 15, to be able to plug that back in there and say, does that make a material difference in where you're, what you're going to do? Again, if you're looking at that, in that sweet spot number of facilities.
Yeah, I'd actually say that the order of that would be reversed. I mean, typically if you have like fundamentally different costs, whether you're going 50 miles to the west instead of 50 miles to the south, that needs to be built into the inputs itself.
Okay.
So whereas in this example, I just give a flat 15 cents per mile, really what the actual table inputs is just saying from this plant to this distribution center or this distribution to this customer costs X dollars per unit, however you devise it. And that's where those conversations around intermodal versus, full truckload versus LTL, that's where that all comes in.
Okay.
Yeah, that's where it's good to see some of those input pieces because like you said, it's not going to be that simple.
Well, it's like how many, again, if you're looking in a region, it's easier. If you're looking in a region, it's easier when you start going global and saying, okay, do I have 2 national, 3, 4? And then it's like, well, then where those places are going to be, how many of those factors do I have to kind of, because you could have, many, many regions. But again, if that's part of the function, then you're just trying to identify that. And then you can go back and fine tune some things afterwards, as part of what I was trying to get at as well.
Yeah.
Okay.
One question that came in online, Ralph, looking back at your fleet management example, Stu was wondering, so on that example, how did data help them determine an inventory strategy for the 90% of the SKUs that were 10% of the usage? So can you talk more about kind of what data was needed for that and how did that help with that outcome?
Yeah. So even though the data required some cleanup, they actually have pretty exhaustive records of their consumption. And so essentially it just said, hey, we use part 1, 2, 3, 4. It got put onto a vehicle. This is the date and the timestamp. And so that was actually pretty straightforward in being able to say, now, what is your consumption by part? Let's aggregate it by the day or by the week. And then you can do that statistical modeling to say, okay, now over the course of a week, some weeks you used none of them. Some of you used 1 unit, some you used 20. So what's the 90th percentile of potential demand over a week? If your service level goal is 90%, okay, that means the 90th percentile of that is how much you should have in stock. That's how I did it.
Great. Another question in the room.
Make you walk all the way across. So also on that example, I'm curious, what would the end audience be for something like that, and how would they interact with this data? Because especially with this inventory, it's a moving target, right? It's not a one-time analysis. We're going to open a distribution center and not evaluate it. So yeah, what is the end audience, and how would they interact with that data, and what would you deliver so they could continue to evaluate?
Yeah. I mean, in most organizations, whoever's responsible for IM and whoever is responsible for procurement, we need to be working together. For this particular one, they really didn't have an inventory management component at all. So it was kind of just individual locations. They buy when they think they need to buy. And that's kind of what happened. And so this was more of a exploratory, like, this is what you can actually benefit in terms of readiness levels for your fleet and inventory levels for the repair parts if you were to adopt this kind of thing.
One question I have, Ralph, is especially now that you're working with outside companies, how are you helping them through data quality? So as you're seeing data that you're getting from them, what are some things that you're asking them for in terms of getting to that? And how are you identifying some of that as this is new data for you coming in?
Yeah, well, I'll address the second part first. One thing I always have going into any sort of new circum is, like, I want to talk to as many people as possible, and I will read as much as I possibly can. So projects, I'll start with whoever my main contact is. I said, please give me a list of 20 people that I need to talk to across the organization that might be tangentially impacted or use this kind of information. And so you just learn a ton going that way. And each of those people will send me whatever new hire decks they have, and so forth. And so that's just kind of learning more and more as we go along. In terms of the data quality components, a lot of it is, to be honest, text issues. So for example, try to think of a way to obscure one of them. I have a cell phone holder. What are all the different ways that you can take a cell phone wallet and put that into words and put that into some sort of database? Well, you can put the full words cell phone wallet. You can use the letters CPW. You can put the letters CPW black. You can put cell phone, comma, holder, comma, black, comma, pleather. Like, there's an infinite number of ways that you can describe the exact same thing. But computers don't know that those are all the same thing. Right? And so that was actually a data quality issue that I encountered recently. Was the same product, and I knew it was the same product because I can read and compare. They were just listed in 100 different ways, and a lot of it's just, I try to partner with data analysts internally if they have a data analyst to say, this is what I did, these are some of the problems I've had, this is how I maybe standardized a product name, so that instead of having 30 different versions of the same product, we're now just calling this black cell phone wallet for the purposes of the analysis. And it goes back to data management, a lot of that.
Yeah, I think a common one I've run into in the past is location data as well with that same thing. So you've got, Rogers Street, Rogers Court. Oh, they're both your location. They look like two locations in your database. And so, yeah, just identifying the text issues as much as anything. It's great advice.
Yeah, and mapping to the extent that you can map location data right off the bat. You find out a place that says it's in Georgia, but it's actually in Minnesota. Probably wrong. One of those is wrong, either latitude and longitude or the state.
Great. Any last questions for Ralph? All right. Well, thank you so much for coming and joining us today, Ralph. Really appreciate it.